Hello, very good evening. Today we are going to have the live session number six, number five. So, I welcome you all to the chemical crystallography course that has been taught by Professor Anshman Roy Choudhury from IISER Mohali. I'm the TA, PMR scholar from Department of Chemistry, IIT Hyderabad. I'm Sayani Burman. I'll be taking, and I am taking the live sessions since a month. Uh, and in this week, week five, Sir has taught us about the reciprocal lattice, how Bragg's law holds the reciprocal lattice, and from where systematic absences are getting generated, and about the crystallization methods and several there are several methods Sir have mentioned. So yeah. So today we'll be solving few problems on past weeks and also about few on this week also. So the first question is, what are the intercepts of the plane with Miller indices 235 in the cubic crystal structure? So we know if Miller indices are 235, then intercept will be just the reverse of it. It will be 1 by 2, 1 by 3, 1 by 5. Now, Miller indices cannot be normalized, but intercepts can be. So we have to take the LCM and we have to do the math. So if I take that, the LCM would be 15, and then each one will be 15. Sorry, it would be 30. Then each one, this first 1 by half term would be 15. Then 1 by 3 term will be 2 into 5, 10. And the 1 by 5 term will be 23, 6. So this would be the answer. The intercepts are 15, 10, 6. So the first option. Just let me do that. So the next one is for copper K alpha, resolution of 0.6 is Armstrong is obtained for which 2 theta value. Okay. So applying the Bragg's law, in lambda equals to 2DHKL sine theta. Now for maximum thing we consider n as 1, then we need to determine the 2 theta value. Then I am taking sine theta in the left hand side. Then it would be 2DHKL by lambda of copper. Now, DHKL for a genuine crystal lattice, it's considered as 1.2 Armstrong. That's equal to the equivalent of the X-ray. So 2 into 1.2 Armstrong divided by lambda of copper is what? It is 1.54 Armstrong. Then this answer would be, okay. So this one would be, if I cut it by 2, 0.77. So it is 12 by 7.7. Okay. This is 1 by sine theta. Then sine theta, sorry, let me write only theta. Then theta would be sine inverse of, if I inverse this also, it will come around 1.17. And we know the theta value of the sine theta value can maximum goes up to 1. So this is invalid. Okay. Yeah. Okay. So this resolution of 0.66 Armstrong cannot be achieved by copper K alpha resolution. Then the next one is maximum resolution, which can be obtained in molybdenum K alpha. Same formula we have to apply. N would be for max, N equals to 1. Then lambda equals to 2D HKL sine theta. We need to find out about the maximum resolution DHKL. Okay. Then DHKL would be lambda of molybdenum divided by 2 sine theta. Right, and sine theta max is how much? Theta is can be 90 degree, and sine theta value maximum is max is 1. Then lambda molybdenum by 2. And lambda of molybdenum, the wavelength is 0.71 Armstrong divided by 2. So this comes around 0.35 Armstrong. This is the maximum resolution can be obtained by molybdenum K alpha using as a source. The next one is what is the minimum value of interplanar distance required for Bragg's diffraction. So this will be the same. The formula, the okay, I'll just write it. DHKL equals to applying the Bragg's law only. It is lambda by 2 sine theta. This is also minus 1. The minimum value of sine theta can be minus. So lambda by 2 is the answer since minus cannot be like we can't assign the distance as a minus sign, so it would be mod and it becomes lambda by 2. So this is the answer. In Bragg's law, theta is the angle between normal to the parallel lattice planes d distance apart and incident rays. Okay. So what like how the Bragg's law is generated if these are the planes. Let's take this is the distance, interplanar distance d. This is the incident ray and this is the diffracted ray, right? Then the incident angle is theta. Now, if this comes here, then the diffracted angle is 2 theta, right? This is diffracted angle, diffracted angle. This one is incident angle. Okay. Now, so theta is the incident angle basically, but here it is written theta is the angle between the normal to the uh, parallel lattice planes d distance apart and incidence rays. No, it's not. They're saying that this is theta. No, this is not theta. So it is false. 100 and 001 are opposite to each other. Okay, let me draw first. I'll just draw. Okay, 100 direction. In a okay, this is x, this is y, this is z. Choose another point. So this is one amount. And 00 in y and z as 00 means it's parallel. 100 is this, 100 and 001. Only in z axis it's 1. This is 001. These are not the opposite ones, rather 100's opposite one would be 1 bar 00, and this ones would be 001 bar. That is, this one would be this 001 bar, and this one would be here around here. This 1 bar 00. So these are not the opposite ones. The next one is the half is a lattice point in BCC unit cell. Yes, in the BCC unit cell means what? Means there should be a body centered lattice, right? So there are 8 atoms in the corner and at body center, sorry, and in body center also there is 1 atom. And if this one is 000, then this one is half, half, half. This is the center one. which is not the equivalent point in P2 by M space group, assuming B axis is as a unique axis. Okay, we have to draw P. Okay, just one second. Yeah. P2 by M. So P2 by M, B axis is unique axis, B axis, and 2 by M is considered two-fold rotation is along B axis, two-fold rotation, and these are the mirror planes. Okay, but 2 by M means M is perpendicular to the two-fold rotation, means M is perpendicular to the axis. Now let me put first the translation related objects. Now two-fold rotation means it will go 180 degree below the plane. This one. Now, a perpendicular M means this is M. Let's say this is B, this is A. So on A axis, it's the mirror is be perpendicular to A, parallel to A axis, and perpendicular to B axis means it will be the mirror reflection. Okay. So if we do the equivalent positions, this one is the first one. This would be the two, and this is inside the unit cell lattice. We can consider this is three. Okay, just I'll just do that. This is inside the image cell. This is one. The reflection of it is two, and the mirror image of it is inside the image cell is this, and the two-fold rotation is this. So the first one would be x, y, z normal. Now we are applying two-fold rotation parallel to y-axis. Then it would be x bar y z bar. Now on this, if we apply mirror perpendicular to y-axis, then it would be x, y bar, z. Now similar to fold rotation parallel to y-axis, it would be x bar, y bar, z bar. And these are related as the mirror plane perpendicular to y-axis. Now you can see another symmetry center of inversion is generating. So yeah. So what are the options? The first one is so the 4z equals to the equivalent points. First one is xyz. It's nowhere in the option. The second one is x bar y z bar. It is here. X y bar z, x y bar z. This one is this, and x bar y bar z bar. This one is this. Okay. Then which one is not the equivalent point? This one is the not equivalent point. X bar y bar z. The next one is what is the space group of the following representation? Okay, from the representation only you can see there is a screw axis. So from like in all the options there is screw axis. Now 1/4 shift of origin. P21 is a simple one. P2 1 by M, P2 1 by C. Nowhere 1/4 origin shift is happening, but here it is happening for P21 to 1 to 1. So the answer would be this. Now I can explain why. See, this is inside the lattice cell, no? So, if I draw the, okay, if I draw this one, like if like, I want to simplify this one. There's a 2 1 screw around, along B axis, okay? And is 1/4 above the projection plane, okay? This is, you can write 1/4 here, 1/4. And also there are 1/4 projection along A axis also, 1/4 origin shift. And this is okay, this is A, this is B direction. So in A direction it's already written. Now in Z direction or C direction is actually perpendicular to the plane of projection. Hence it will be here. Okay. So let me draw first the translation related objects. Now, since 2 1 screw is applying along B axis, the first 2 1, see, this is P 2 1 2 1 2 1. So that there are three 2 1 screws, and all are, then the three are respectively along the ABC axis. Let me take first about the B axis. Okay, if it is here, then it's like 2 1 screw means two-fold rotation. It will be here, right? Then along translation, along this direction, half translation. So it will be here, right? Let me erase this. Okay. Similar way for this one, it will be here. Okay. Now another 2 1 is along the A axis. So let it be this one. So if it translates more, then it will come around here. So another screw axis is getting generated. Okay. Okay, I'll just draw this one, and another screw axis is this is another screw axis along B. So this one is getting generated, half translation and two-fold rotation. Now this one is outside of the unit cell, and if I want to include it inside the unit cell, we can add just +1, and it will come here. Okay. So what are the now we can say that what are the equivalent points that we are getting generated? One inside the unit cell only. One. Let this is two. This is three. This is four. Then one is XYZ. Two is half plus X. Like uh, translation along A axis. Then along Y axis also it's been translated half. Then in Z axis, and it's Y bar and Z bar because the translation is because yeah, the rotation is along the X axis. The 2 1 is along X axis. Similarly, the three-fold rotation, the equivalent point would be Z bar plus half, and the fourth one is X bar plus half, Y bar plus half, Z. These are the four equivalent points of this P2 1 2 1 2 1. Okay. So the next question is matching the correct options. So first bracket means it's what? First bracket means it's crystal planes. The Miller indices how we denote as in first bracket only. So the third bracket is equivalent planes. So A3, okay. B1. So the first option is the correct one. We'll just check the another options also. So the this brackets lesser than and greater than brackets. These are what? These are in equivalent directions. Yeah, and the these ones are okay. These are crystal direction. These are crystal equivalent planes. That's what I'm thinking. Yeah, these are equivalent planes, and these are crystal directions. So the option would not be this, but be D is 1. D is 1. So this one. Uh, what are the Miller indices of the following plane? Let's first write about the intercept. Intercept in X, Y, Z axis. In X axis, it is half. Y axis also it's half. Z axis, it's 1. 1. Then the reverse of it or Miller indices would be the reverse 2 to 1. 2 to 1, yeah. This one is the option. Now identify the correct plane for the Miller indices. Okay. For 110. Okay. 110 means the intercept would be, see, Miller index is 110. Then the intercept would be 110 only, the reverse one. So 1 along x-axis, 1 along y-axis. That's it. So this is the 110 plane. 110. The next one is CMM2 group has, okay, space group has z equals to 6. So we have to draw the CMM2. C means C-centered lattice, right? So we can draw it like this. We will draw first the translation related objects. And there is the C1. Okay. Now this is M. This is the M. So this is also M getting generated here. So it will be, for here also it will be the same for all 4 points. Now we have to detect the equivalent points. So let's inside the unit cell only. For see, for the C center one, you can see this is 1, this is 2, this is 3, this is 4. Okay, and just first detect the primitive ones. Okay, the corner ones. So this is 1, this is 2, this is 3, this is 4. Right. And here for C centering, it is 5, 6, 7, 8. So 1 is X, Y, Z. Now if it is M perpendicular to Y axis, so this is Y, this is X. Let's first take M perpendicular to X, right? Because we have indicated this is 2 and this is Y axis and X axis is perpendicular to Y, right? So M is along a Y axis means M is perpendicular to X axis. This is X bar, Y bar, Z. Then M perpendicular to Y, X, Y bar, Z. And a twofold rotation along the Z axis. So the Z axis means here. So it would be X bar, Y bar, Z. Now the second one is, we have to erase this. Second one is the for C centering. It would be X plus half, Y plus half, Z. Now what happens if it is, okay, I'll just leave this. Okay. So now, if we apply m perpendicular to x, it would be x bar plus half y plus half z. Then again m perpendicular to y, x plus half, y bar plus half, z, then 2 along z axis to full rotation, x bar plus half, y bar plus half, z. Hence, z equals to 6. Here it is written z equals to 6 only. Okay, then it is true. Now the next one is following space group representation has z equals to 16. Okay. See, you can see from here, this is a C-centered lattice. Okay. And how many are there? One. Like we'll count inside the unit cell only. Okay. So it will be 1, 2, 3, 4. And from C-centering also 1, 2, 3, 4. Right. Okay, there is another one. Here also 1, 2, 3, 4. 8 has been done. 9, 10, 11, 12, 13, 14, 15, 16. These are unique. Okay, let me do again. See, for C centering also you can see 1, 2, 3, 4. Right. Now for primitive one, you can say 1, 2, 3, 4. See, these are all different, right? 5, 6, 7, 8, 9, 10, 11, 12. So there should be 16. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. Yeah, it's true. Yeah, you can count that there are all different equivalent positions, right? So the next one is Miller indices of direction 1, half, 1. Okay. Half, half, half is this. Now, Sarah taught us that it would be tip minus base. Tip minus base. So means half, half, half minus 1, half, 1. So it would be minus half, 0, minus half. Now, if we just do the like LCM, then it would be 1, 0, minus 1. Okay, minus 1, 0, minus 1. So this is 1, 0, 1 bar. So this is not the similar direction. Okay, this is not the similar one. It's false. Planar density of 110 plane of FCC lattice is pi r 5 4 root 2. Okay, so we'll just draw here. Okay. Now 110, we have just seen what is 110 plane. This is 1, this is 1. So this much is 110 plane, right? So in this plane, and what are the atoms placed? Here, 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 here. And in this plane, I'm just drawing in two faces. Here, in this face also. in the back face also, and in the front face also. Okay. So I'm just like giving the solid circles in for the points which the 110 plane contain. Okay. So this is the plane. Now, the what will be the face of the plane? If it is the face, then there is one circle. There is this, there is this, this. Right, you got it, right? This one is, this one is, this one. Then this one is, this one, this one is, this one. Similarly for the lower surface also. Now, this much is r by fourth. This much is also r by fourth, but this much is 2r, right? So now for FCC lattice, what happens is in for FCC lattice, if this much is A, then this much would be what? Root 2A, phase diagonal, right? Then what we can say for this surface, the surface area is, this one is root 2A and this one is A. A into root 2A, that is root 2A square. And the area covered by the atoms is, there are 4 pi r square by 4, right? If we consider the areas of the corner atoms, then it is pi r square, right? But it is just the one fourth of it. So we can say, okay, this is not the correct one. What I wanted to tell is, this is the one fourth of the circle. This is the one fourth of the circle, and this one is a semicircle. This one is a half semicircle, right? So one fourth. So here for the area covered by atoms, it would be, there are four such one fourth circles, right? So for one circle, the area is pi r square. Now, for 4 circles, it is for 4 pi r square, but it is the one fourth of each circle. So it is pi r square by 4. Now this nullifies, and for the center circle, for this one, it is pi r square by 2, because it's two semicircles, right? And how many are there? Two. So it also nullifies. So the total is 2 pi r square. Now for a face-centered lattice, what is it? Root 2a, you can write root 2a equals to, this much is, okay, this much is r, this is 2r, this is r. So 4r, right? Then r, okay, r equals to root 2a by 4, right? Then the planar density equals to area, I can write, by the surface area. Atoms area how much? 2 pi r square by root 2a square. Now from here we can write r by a equals to root 2 by 4. Right. Then it would be this one, root 2 pi into r by a whole square, means root 2 by 4 whole square. Right. Then we can write root 2 pi into root 2 into root 2. That means it's 2. 2 and 4 into 4. This is 2 and this is also root 2. So it is pi by 4 root 2. And the question is also 5 by 4 root 2. It is true. If the Miller index, next question is if the Miller index is 0, the plane is perpendicular to that axis. Miller index is 0 means the plane is parallel to that axis. Not, it would be parallel. Then this is the false statement. The next one is the PXRD pattern is more spread out when we use copper radiation instead of molybdenum radiation. Sir has already taught us, Sir has derived also. I'll just tell one thing that we know the copper K alpha, the lambda of copper K alpha equals to how much? 0.71 Armstrong. And for lambda of molybdenum K alpha, it is 1.54. Sorry, I have reversed it. It is 1.54 Armstrong, and for molybdenum, it is 0.71 Armstrong, right? Now we can see this is, then we can write from here lambda of copper is greater than lambda of molybdenum. Or if E equals energy equals to Hc by lambda, right? Then energy of copper is lesser than energy of molybdenum. Means molybdenum is more energetic or more powerful. Hence, molybdenum can penetrate any crystal structure the inter plan the planes, the lattice planes more, right? And if it is if the penetration power is more, if the penetration power is more, then due to the increased penetration depth of this higher energy X-rays, the diffraction signal will come from deeper layers within the samples. Okay, more penetration power. I'll just write here. Penetration power, more penetration power means diffraction signal comes from deeper layers. Right. So generally, sir has already taught us. So lambda, I'll just write it here. Lambda copper alpha by lambda molybdenum. It's lambda is proportional to from the Bragg's law, and lambda is proportional to sine theta. Right. It's sine theta copper by sine theta molybdenum. So if we do that, then the copper K alpha 2 theta range comes around 5 degree to 70 degree 2 theta, and the molybdenum K alpha comes around 2.3 degree to 30.66 degree. So you can see this range is shorter, right? Then the PXRD patterns will come in the short region, whereas for the copper K alpha it will be spread out. So this one is false because the reverse one happens. No, no, sorry. The statement is correct only. Yeah. PXRD pattern is spread out for copper only, right? I just told you. So it's false. So it's true. Now the next one is systematic absences in the X-ray diffraction pattern will allow the space group of the crystal to be assigned. Yes, there is no problem in it. Now Bragg's condition is not satisfied for the reflections undergoing systematic extinctions or absences. But Bragg's condition is a basic rule, basic principle for the any diffraction, right? So it's false. The purity of solution affects the rate of crystallization. Yes, if the if the solvent is pure, then it crystallizes wisely, and if it is there is any impurity, then the crystal may not come as pure, or the crystal structure varies, or you may not get the ordering and all. So it affects, yes. Now the next question is, which of the following reflections will be absent for a BCC lattice? Okay, for a BCC lattice, for systematic absence, the rule is H plus K plus L, the sum of the Miller indices should be odd. Okay. Now this is the sum is 3 here, the sum is 2 here, the sum is 6 here, sum is 6 here. So this is the option. For this 111 plane, the 111 reflection, for BCC lattice, reflections will be absent. Now, the next one is the orthorhombic space group PNMA will have systematic abscences due to. Now, from this space group, you can see this is primitive lattice, N glide, M mirror, A glide. So, there are glide planes present. And so, here from the option, you can say glide planes, right? So, this is a primitive lattice. This option is getting out. Now there is no, this is a chiral space group, right? So there is no center of inversion. This option is also out. Now screw axis, there is no screw axis. This option is also out. Now the next one is crystallization can be used as a purification technique based on difference in pressure, difference in solubility, difference in melting point. So the answer would be what? So the answer is difference in solubility. Right now I told that if it is more soluble, then you'll get a different kind of crystal, and if it is less soluble, you'll get a different textures of crystal. The next one is, which among the following affects the process of crystallization? Slow cooling. These are like impurities, humidity. Yes, all of the above. And the next one is, a crystal suitable for data collection should have irregular shape. No. Dimensions larger than the diameter of X-ray, no, then how will you collect the data? Only no refraction will happen. Very high mosaicity. Mosaicity means the lattice plates are not in perfect order. Like they are in order, but they're imperfectly ordered, right? So no, this is not suitable. So none of the above. Crystallization is governed by thermodynamics, kinetics, yeah, both thermodynamic and kinetic factors. Right, kinetic factors in the sense slow cooling, fast cooling, thermodynamic, you can say the about the solvents, the solvents we are using for that. Okay. So this was about this week's lecture. And the week 5 assignment is already there in your portal. The last date is 30th August. Okay. Please submit your assignments. Thank you.